In this video, we are going to show that the last two digits of 9 to the power 9 to the power 9 to the power 9 is equal to that of 9 to the power 9 to the power 9. Before we move on, don't forget to give a like, subscribe to our channel, and turn on post notifications. There is a very useful tool when the number that we are dividing by is another perfect power. 400 is 10 squared, and it's really hard to keep multiplying 9 by itself and try to observe the pattern, because when we do say mod 100, there are 100 possibilities, so we might need to do multiply many times to find to wait until the pattern appears. And coincidentally, the base of the power at the other side, that's 9, and it's actually really close to the base of the power that we are doing mod on, and that's 10. So there's a very useful tool on this, which is to use the Binomial Theorem. To do this, I'm going to start off with a slightly easier example, just 9 to the power 9 to the power 9, this one. I'm going to rewrite that as 10 minus 1 all to the power 9 to the power 9, and I'm going to expand it with Binomial Theorem. So as we know, we start off with 10 to the power 9 to the power 9, and then the exponent of 10 goes down by 1, while the exponent of minus 1 goes up by 1. So in fact, there is something like minus 1 to the power 0 here, but that can be ignored because it's just simply 1. And next to these product of powers, we have to add the binomial coefficient, and that depends on the exponent of one of the powers. So for this, I'm going to choose 9 to the power 9 minus 1 and multiply that, and we keep going. So in the next one, the exponent of 10 goes down by 1 again, while exponent of minus 1 goes up, and the binomial coefficient becomes 9 to the power 9 choose 9 to the power 9 minus 2. And we'll just keep iterating until the exponent of 10 becomes 1, say 1, and then for that of minus 1, it becomes 9 to the power 9 minus 1, and the last one is 0, and minus 1 takes up all of 9 to the power 9. While for the binomial coefficient, the second last term is 9 to the power 9 choose 1, and the last term is just 9 to the power 9 choose 0. Again, that can be ignored because it's just simply 1. In fact, I've even omitted that of the first term, but that's fine. So now after expanding, don't forget we are actually trying to do mod 100. So for the starting terms, we have powers of 10 here, and they are all clearly multiples of 100 because the exponent is way larger than 2. So that means for all terms with the exponent of 10 to be at least 2, I can just regard them, I can just take them as 0 under mod 100. So that means all terms, all of these terms can be written as 0 under mod 100, each of them. And so the sum is also 0 mod 100. And so what remains is just to look at the last two terms. And that's why I chose Binomial Theorem, because that makes things much easier. Now for the last two terms, the second last one, 9 to the power 9 choose 1, is just 9 to the power 9 times 10, while for the index here is an even number because it's odd number minus odd number. So it's just times 1. And as for the last term, this one is a 1, this is a 1, and this is a minus 1. So you just say that for these two terms, it's that product 9 to the power 9 times 10 minus 1 mod 100. And from this we can see that we can do the same on the more complicated power. And in fact, I can say it's also congruent to 9 to the power 9 to the power 9 times 10 times 1. Okay, it's the same, minus 1 mod 100. And from this, if we want to show that the last two digits of both powers are the same, it only means to show that these two terms are the same have the same remainder when they divide by 100. But that is quite approachable because both terms end with 0, so we can just ignore the last digit and focus on the second last digit, the tens digit. Or, in other words, looking at this, mod 10. And for this, we can look at 9 to the power 9 to the power 9 mod 10. But that's much easier because when we look at powers of 9 mod 10, there's a very simple periodic sequence. Start from the first one has the last digit to be 9, the next one is 1, and then it repeats itself. And so that only depends on the parity of the exponent. And because 9 and 9 to the power 9 are both odd, so that means both are congruent to 9 mod 10. And so there we have our desired result. Furthermore, if we want to really calculate the last two digits of these two powers, then from this we know that both blue terms, say 10 times n plus 9, and then multiply by 10 minus 1 for the first term. And so there's 100 times big N plus 89. Of course, for this, you can let the power to be 10 times big M, but that's the same. It's just a different expression, but the last two digits are the same, and that is 89. These two powers both end with 89. Please feel free to share your ideas in your comments. Thank you for watching. See you next time.